Hello guys, this is Niraj, studying in IIT Roorkee. I am from the EPS branch and currently in third year. This video presentation is a part of the course Applied Instrumentation, and in this video, I'll be quickly overviewing the topic detection of radiation or various sensors that can be used in detecting any radiation. To begin with, let me explain you guys transducers and sensors. So transducers are devices that convert one form of energy into another. Consider a block diagram in your mind. So the block being transducer. Input to this block is one form of energy and output is another form of energy. So to give an analogy, the input energy may be mechanical energy and output energy may be chemical energy. So this is the basic principle of a transducer, that it converts a one form of energy to another. Now, speaking of sensors, sensors are subsets of transducers. That is, sensors convert one form of energy or change in environment into electrical energy. So the differentiating point between sensors and transducers is that the output of sensors is always electrical energy. To get more views on sensors, let's move to the next slide. Yeah, so as I said, sensors convert any physical stimuli or change in surrounding to measurable signal or electrical output. So as this GIF shows, this sensor uh, converts the motion of the block into electrical energy. Now this is a typical sensor, but there are different sensors which can be used in daily life, such as temperature sensors, proximity sensors, IR sensors, and these have different applications. But the principle is same, that it converts one form of energy into electrical energy, which is detected. Now, as my topic is detection of radiation, let's see what are different types of radiation that can be detected. So the major categories of radiations are charged radiation and neutral radiation. So as the name suggests, charged radiation will comprise of charged beams. So that is proton beam, electron beam, alpha radiation, that is of helium atoms, etc. And neutral radiation will consist of photon beam and neutron beam. Neutron beam will comprise neutrons, and photon beam may be of visible light, gamma rays, X-rays, cosmic rays, etc., infrared rays, etc. Now, these radiation are to be detected. So let's see how these radiation will interact with matter. Because to get detected, they should interact with matter, that is the sensors. So interaction of these radiations. So what happens is when the charged particle radiation enters matter, it experiences a Coulombic force due to the atoms present in the matter. So the electrons in the atoms apply a Coulombic force on the charged particle radiation, thus causing changes in the matter which are further detected. However, this won't be the case for uncharged radiation. The neutral radiation undergoes a catastrophic interaction with the medium, that is, they undergo scattering in it, such as in elastic scattering, absorption, etc. And for particularly gamma rays, we can see photoelectric effect, Compton scattering, and pair production. Now let's say different types of detectors. So different sensors for detecting radiation. There will be various detectors and sensors that can be used. But as I said, I am giving a quick overview of the topic. I'll be explaining only three sensors detectors here. So that is ionization chambers, scintillation detectors, semiconductor detectors. So what are ionization chamber? As the diagram shows, there is a chamber which is connected in the circuit. The chamber consists of a gas, so the incoming radiation interacts with the gas. So what does that mean is the charged particle radiation ionizes the gas to produce an electron and positive ion pair. And due to the circuit present, there is an electric field that drives these electrons and positive ions to the plates of the chamber. Now, this generated pair is further driven to the plates of the chamber, creating an electric pulse which, after undergoing through signal conditioning unit, can be detected. So, as I said, the electrons and positive ions created through the charged particle radiation are driven to the plates of the chamber by an electric field. And using proper statistics and signal conditioning unit, we can detect this radiation. Next is scintillation detectors. So let me begin with the word scintillation. What does that mean? Scintillation or scintillate is flash of light or sparkle. This can be of two types, fluorescence and phosphorescence. So fluorescence is when incident light shines the media matter, we get a spontaneous response. That is, When light shines the matter, we get a quick output of light. Whereas in phosphorescence, we get a delayed output. That is, when we shine any matter with incident light, we get a delayed response or a response for a long time. This is known as scintillation. So how these are used in the detectors. So the scintillation material absorbs the incoming radiation to produce light. These photons then pass through a photocathode where they are converted to photoelectrons and then amplified using PMTs and finally are detected. So scintillation materials can be of various types, organic and inorganic. They are classified based on the response time. So inorganic scintillators have a response time of microsecond and organic scintillators have a response time of nanosecond. And as the diagram shows, scintillation photons are produced when the electron de-excites from the activator excited state as shown in the diagram. So this is a schematic diagram of scintillation detectors. As the red line shows, the incident particle shines the material, thus producing light. This light, that is photons, pass through a photocathode to produce photoelectrons. Now, the produced photoelectrons are very small and not detectable. So we need to amplify it. For amplification, we use PMTs, that is photomultiplier tubes. The typical output of PMTs is 10 to the power 6. So for one electron, we'll get 10 to the power 6 electrons. And the working principle of PMTs is that the electron falls on the dinodes to produce further electrons and thus the cycle continues. Lastly, I'm going to talk about semiconductor detectors. So the radiation interacts with the semiconductor material, imparting its energy to produce electron-hole pairs, which are further converted to electric pulses using proper circuits. These detectors have better resolution because the carriers produced in these materials due to incoming radiation is much larger than the other detectors. Also, scintillation detectors and semiconductor detectors are a bit better because the material in these detectors have higher density than ionization chamber, and thus the interaction sites are larger than ionization chambers. So now you guys can ask me about what about visible light and other photon beams. So these beams also interact with the semiconductor detectors to produce electron hole pairs, thus changing the conductivity and resistance and can be detected. And in neutron beams, the neutron beams interact with the material to produce charged particles or gamma rays, and further, these gamma rays or charged particle radiation can be detected from the same principle that I have explained. This is a typical output of the semiconductor detector and scintillation detector. So as you can see on the left side, we have the semiconductor detector output, while on the right side, we have scintillation detector output. And the resolution of semiconductor detectors is far better than scintillation detectors. Finally, giving the references, as I said, this video is just an overview of the topic. I have not went much into details. So you can dive more into this topic using these references. The first reference is Radiation Detection and Measurement book by G.F. Knoll. Second is Wikipedia. And third is obviously ChatGPT. It has made it easier to search various topics. Yeah, thank you. I hope you guys like the video.